So I'm going to try to show in a couple of steps how to do it and why most of it, I guess, works. I found this very difficult to understand at the beginning, but now it kind of makes sense. So first, there are several assumptions that we make. The assumptions that we make are that all the collisions are elastic, that there are no intermolecular forces, and we assume that the time between collisions is less than between collisions. We also assume that the pressure and force is the same around the whole container. Each molecule is identical. And traveling the same velocity. We also assume that the molecules travel in straight lines and that movement is random and that the laws of physics exist. We obviously do. Okay, so these are sort of all the assumptions. I think the ones that are key that you'll probably be asked is that all the collisions are elastic, meaning the kinetic energy is conserved. There are no intermolecular forces, which essentially links to this one. So there's no bending around particles because of the forces. And this is one of the key ones for just ideal gases. Yeah, and another one specifically for just ideal gases is that they don't change state. Yeah, that's another key one that I keep forgetting, so I need to remember it. Anyway, so you can write that down or whatever, and I'm going to rub it out because we got to get to the actual kinetic theory of gases derivation. So we have this cube, so we're assuming the gas is in a container, it's traveling at the velocity of x, which we're going to call this particle x. But it's traveling at velocity x. This is length x, length y, and length z. When we calculate pressure, we're going to use this kind of panel, because that's where it's hitting on. The particle is going to hit on this wall and going to travel back. So there's a lot of things we need to consider. So first of all, we need to consider the force of this particle, which you use F equals ma. I'm using the second law. So the force equals the mass times the velocity of x divided by time. And right now we are talking about one molecule in container. I know cont technically means continue, but yeah, anyway, in one container. In this container, we're only considering one. So then, the next thing that we need to consider is the elastic collisions. So basically, the collisions with the wall. So when the particle is traveling towards the wall and away from the wall, and if we say that this direction it's going in is the positive direction, then it going the other way is the negative direction. And because the change in the velocity is the final, take away the initial. The final is negative x, take away that. So this would equal negative 2 vx. It's just considering that it's going in two directions. So here I should put the change. Silly me. Then we also need to consider the time that it takes. So we think about the equation of velocity, which I know is technically displacement over time, but we're going to do distance divided by time. The distance is Lx twice, just divided by normal time. So time would equal 2Lx divided by Vx. Okay, so now we're going to combine some of these things together. Combine this, we're going to combine this, and we're going to combine this. Then the third thing we need to also consider is the pressure of molecule. Pressure for the area is Ly times Lz. Substituting this into this equation, so essentially the equation is this: PV equals negative mx squared. But technically, you can't have negative mass, and this is squared anyway. So we can remove that negative. Okay. So this is sort of the first part. This is considering one molecule. Okay, so if we move on, we have our equation. Now we have to consider all directions. Find a average speed. We take, let's say, one particle going in x plus another particle going, let's say, x direction. And the reason we square it is so that we know that all of these numbers are positive. So then that's just like continuing until just n. So we find the total amount of speed in all of the molecules, and we divide it by the amount of molecules there are. And this is also square rooted. So then what we do, because we want to use the average speed of all of them into our big equation, so we have PV, wait, what have I done here? It's doing me. PV equals, I'm going to put it here, so you want to times it by all of the molecules. Then we have our M from up there, and we have our, because this is squared, would mean, I suppose like if we sort of used the average speed, so if we have sort of this is like V total, that would be V total, where this is in brackets by the way, which is why this is equal to the V root mean squared. So then we're almost there. PV equals N M V root mean squared. Or root mean speed or whatever, and it's squared. I just call it root mean square, I don't know why. Anyway, so then one more thing we have to do is we have to think about the V root mean speed squared, but of the total, which would include the V Z, where this is all squared by the way, equals 3. Because we assume that all of these are identical, we could just sort of call it one thing. So let's just all call it x. Where this would then be a third if we divide everything by 3. Therefore, the total of everything, there you go. That's like the total kind of kinetic theory of gases. So this is sort of saying like, this is considering every single molecule in this specific container with a specific volume, the specific number of molecules in it, going all at the same speed with the same pressure on every point. And yeah, I hope you found it useful.